This video lesson is on acid equilibriums. So there's two things that we need to consider when we're looking at acids, whether the acid is strong or whether it is weak. So if it's a strong acid, basically what happens is it ionizes almost completely into anion and into H+. What does that mean? Well, basically based on this little diagram here, HCl will get converted completely to H plus and to the ion, the chloride ion, or whatever other anion that's present in that acid. And HCl is an example of a strong acid. But weak acids, basically what happens is not 100% of it will ionize into the H plus and into the anion. And so basically the concentration of the acid is not going to be exactly what the concentration of the H plus is. Okay, and it's the H plus that's present in the solution that makes it act like an acid. So we have to use an equilibrium to determine what the H plus concentration is, and therefore figure out what the pH is. Okay, so but in both cases, what we're going to use is the pH formula, which is the negative log of the H plus concentration. Okay, so consider these two examples here. So for a strong acid, what is the pH of a 0.025 mole per liter solution of HCl, which is a strong acid? Well, basically what that tells us is because the concentration of the HCl was 0.025 and 100% of it gets turned into these two components, the H plus concentration is exactly equal to the acid concentration. So the H plus concentration is 0.025 moles per liter. So there's actually no HCl present anymore in the solution. Okay, and so this is actually a relatively easy calculation. We can figure out what the pH is just by plugging in our concentration into the formula, and then from there we can figure out what the concentration. So what we have to do here is actually use the log. So we're going to type in our concentration, press the log button, okay, and then change the sign, which makes the pH 1.60 for this solution. Okay. Now the reason why we're doing this is we're going to compare this to what happens with a weak acid. So in this case, we're looking at acetic acid. So acetic acid is just vinegar, and it has an equilibrium. So here we're going to have to use our ice table that we're accustomed to using. Okay, so this question's asking us, what is the pH of a 0.025 mole per liter solution of acetic acid? We don't know how much is converted into the anion and the H plus, so we need to use our ice table to figure that out. Okay, so we'll write in our initial concentration of H of the acetic acid. This is just a generic version of any weak acid. Okay, it's got the H and it's got the anion that's present. So for acetic acid, we're going to write down 0.025, and if that was dissolved directly in water right at the start, there'd be no H plus and no A minus compared to the anion. But as it achieves equilibrium, we're going to lose a certain amount of the acid, of the acetic acid, and it'll be converted into H plus and into the anion. Okay, and finally, in the last row, we're going to combine these two. So we're going to combine the 0.025 minus x. Okay, 0 and x is just x, 0 and x is just x. So we're going to use those expressions in our equilibrium expression. Now, we're going to use the assumption again, because Ka is relatively small, okay, so this is a small value, we're going to assume that the x is a lot smaller than our initial concentration, and so this expression is going to turn into just 0.025. Okay, and that's going to simplify a lot of the math that we have. Okay, so the Ka, okay, which is a generic equilibrium expression, not like the ones we've looked at before, is always going to be the H plus concentration, so the products again, times multiplying the two products, divide by the reactants concentrations. Okay? And that's the same for every weak acid that we'll use. Okay, and we're just going to substitute these values in. So H is now X, so is A minus, and HA, we're just going to use the assumed value of 0.025 moles per liter. And it's 1.8 times 10 to the minus 5 is our equilibrium value. Okay, this simplifies this a lot. We can move this into the numerator by multiplication. It becomes x squared, and 0.025 times 1.8 times 10 to the minus 5 is 4.5 times 10 to the minus 7. Okay, and then next we're going to take the square roots. So square root 4.5 times 10 to the minus 7, and that's the change in the concentrations. So x is going to be 6.71 times 10 to the minus 4. Okay, and it's going to be in moles per liter. Now, all we're really interested in is the H plus concentration, which is X. So once we know what the H plus concentration is, we can figure out what the pH is by taking the logarithm of the concentration and the negative logarithm at least. And so the new pH is 3.17. Okay? And this is significant because both these acids, these solutions, are at the same concentration. So if they're both strong acids, they would have the exact same pH. Okay? But because this is a strong acid, all of its H plus has been converted, or sorry, all of its acid has been converted into H plus, and so this is more or less the maximum value that it could be. So this is the most acidic this solution could ever be. Okay? Whereas in this example, because it's a weak acid, not all of the acid is converted into H plus, and so we can see that it doesn't achieve that maximum pH value, that most acidic pH value. It's about 1.5 units away, which is at least 10 times difference in their strength as acids, even though they have the same amount of acid present, or same amount of salt, if you think of it that way. Okay, it's just that not all of the acid has been converted to H plus, and so it doesn't behave in the same way that a strong acid would be.